Hello and welcome to yet another lecture from Bayesian Psychometric Models Fall 2022. This is not the class recording. Unfortunately, due to a mistake on my part, the class recording did not have audio. So all of those bad jokes that I provide are lost to the ether of whatever. They're gone. So today we'll have the same content in this recording with fewer bad jokes and hopefully be a little bit more efficient. We are in Lecture 4A, which is an introduction to the generalized measurement models, and we're talking about the latent variable side of a model. In particular, when we had discussed this in our last lecture, we left with the idea that on the left-hand side where the data are, we are modeling a function, that's this F term, of some statistic. Here it's the expected value of observed variables. That's what the left-hand side represents. The right-hand side represents our theory. In this case, we are believing there's one latent variable, theta, for each person p, and we're mapping that onto the space of the data using a linear model itself. So the left-hand side will differ by the type of data, the type of potentially statistic we put inside the function itself, and potentially other features of the model itself. But today is about latent variables and their characteristics. Latent variables are built by specification. That means they don't exist, so we create them. And the key parts of specification that we are interested in particular, are what is their distribution. In practice, nearly all latent variables are normally distributed. There are some places where they are not normally distributed, and we'll get to those a little bit later. But then after we specify their distribution, we also have to specify how we specify their scale, because a normal distribution talks about is for a continuous measure. So any variable that follows a normal distribution can range anywhere on the real number line, negative infinity to positive infinity. What we need to do is determine what the mean of that latent variable is and what the standard deviation of that latent variable is. And in our steps to latent variable analyses, this would be step 2. So once we do that, then we go about creating latent variables by specifying or creating items which are built to measure these variables in an analysis model. So ideally, before you even created items, you understand the construct you wish to measure. That's what the latent variable represents, or latent variables. And then you create items measuring that construct itself. And we denote the mapping of items that measure latent variables by the several different names, depending on the field that you're in. Sometimes we call this item alignment, particularly in educational measurement. Items align to certain educational standards or domains or content areas. In psychology or other social sciences, we may talk about a factor pattern matrix. This comes from exploratory factor analysis, trying to figure out the pattern of which factors that items themselves load onto. And then more recently, this also can be referred to as a question or Q matrix. This term came from a field of diagnostic measurement that Kikumi and Maurice Tatsuoka in 1983 defined this term. But you start to see this also recently used in multidimensional IRT, not just papers, but also R packages. MERT, for instance, will use a Q matrix. So if you were in class today, you saw our alignment task, where we took the 10 items from the conspiracy theory example, which were up here on slides 4 and 5. And we tried to figure out two things. We had to figure out how many latent dimensions underlie these items, and then for each item, which dimension you believe it had to measure. And there were varying discussions about this as well. I'm going to just, for now, describe two. It looked like in those items that many of the items referred to some government entity. So for instance, conspiracy about the government trying to do something that is nefarious, versus perhaps a non-government entity that's causing problems. So for the Q matrix itself, the rows of the Q matrix contain the observed variables, in this case the 10 items. The columns contain the latent variables. So let's call trust in government versus trust in non-government, if you want to think of it that way. So if an item measures dimension, we take one of these values and call it a 1. And if it does not, we leave it as a 0. So we can move from the Q matrix to a model, in this case for an example item, by talking about the alignment specifying which latent variables are are measured by which items. In previous literature language, we may say items load onto factors. I prefer not using this. I like the idea because the direction seems opposite. An item seems to load onto a factor means an item should predict the factor. And as you know, in this type of measurement model equation, the latent variable is actually predicting the response itself. So the directionality it seems to be different by the term load onto. So that's why I use the term measured by. So the mathematical definition of either of these terms is simply whether or not a latent variable appears as a predictor for an item. That's it. That's what the Q matrix is trying to govern. So if we take that first item, going back to it right here, the US invasion of Iraq was not part of a campaign to fight terrorism, yada, yada, yada. We move on down to our Q matrix entry for this item. Because it talks about the US government or the US invasion, implying the government, you could put a 1 there for the government, saying this item measures trust in the government, whereas you could put a 0 otherwise for non-government agencies. So the Q matrix then implies that the item only measures the government factor. And so the model for that first item itself, so item 1, that's the subscript right here, is only a function of that latent variable 1. Also containing the linear model parameters that we're used to, some intercept and some slope that we'll know by different names. In fact, moving forward, the intercept itself, so again, as we had talked about in previous classes, the latent variable, had we observed it, what this measurement model is doing is essentially taking a linear regression, trying to predict a function of the data, a function of a statistic of the data, by this latent variable itself in a linear model. The linear models that we know of before have an intercept, have a slope. We still have those here in this model, only now they go by a little bit different notation, different Greek letters effectively. Mu1 is the item intercept. In typical linear models, that's beta 0. Lambda 1 is the item factor loading or item discrimination. In other typical linear models, this might be beta 1, a slope. Turns out the item intercept and the slope have the same interpretation. The intercept is the predicted value when the latent variable is equal to 0. The slope is the increase or change in the outcome per unit change in the latent variable. So this is the typical linear model. But the key to note on this and in this confirmatory approach to latent variable measurement, that this item only measures one of the factors. And that's what the Q matrix is doing. It's serving to put a constraint in here to remove the influence of the second factor or latent variable on the observed variable that we've collected. So we can play around with this Q matrix a little bit more. We can show how this would work with Q matrix entries. So for instance, let's take this, again, this first function of a statistic of the observed variable, y, and let's write out the linear model with all the possible terms. So here, what do I mean by that? We have our item intercept. We have a hypothetical factor loading for the first factor times the factor score for the first factor for a person, and the hypothetical factor loading for the second factor times the factor score for the second factor. Now the Q matrix, we can take the elements of the Q matrix, Q11 being the first element and Q12 being the second element of that row for the first item. And we can put this in here. And because the Q matrix entries are either 1 or 0, they serve the function of allowing each term in parentheses to exist or not exist for the item itself. So in our item, we said Q11 was 1. So when this becomes 1, we are left with lambda 11 times theta P1 on our measurement model for the item. Q12 for this item was set to 0. So when anything is set to 0, none of this appears in the measurement model. So what the Q matrix is allowing us to do is provide a general form for how we can specify each item's elements or each item's components that can be different from item to item depending on our alignment specification or our entries in the Q matrix. And if you remember matrices, and who doesn't love matrices, particularly on a Friday afternoon as I'm recording this, we could take the Q matrix and we can actually put this directly into the model itself. So for instance, if we took each hypothetical factor loading and put that into a vector called lambda1, right, with the transpose, and we had each hypothetical, or we take the Q matrix and we multiply, we have this diag Q function that I'm talking about here, which is basically the Q matrix times a diagonal matrix of ones, right? So our Q matrix entry for the item was 1, 0. We multiply this together, we're left with this matrix right here. And then finally, we have our theta vector, theta p, and I'm realizing I should have a transpose up here as well. My matrix algebra is a little bit off for notation-wise, but this is effectively what we can do. But what this is serving to do is provide our linear model form as a function of the Q matrix. So if we could code this the right way, we wouldn't have to make a lot of changes in each item by item coding within Stan or whatever program we chose to use. So I had figured out my own personal alignment for these items, and we had, of the 10 items, I picked items 3, 4, 6, and 10 over here as measuring this non-government factor, whereas the rest of the items measure the government factor. So up to this point, we've talked generally about the right-hand side of each item's model. And typically when we start to call different names for different models, this is where you see different parameter constraints come in to delineate some of those names. So what do I mean by that? Well, if we impose the constraint where the factor loadings or the item discriminations, which are synonymous, are equal across all of the items, that is a constraint that would differentiate what's called a Roche model for some types of data. So it's sort of the combination of the type of data and the type of constraints on the factors that provide a model name itself. But for us, because we have to code every line in Stan ourselves, we need to see it from the perspective of linear model components and the types of variables that we're specifying as well. So that linear model version of each item equation I prefer because it not only is somewhat easy to implement, it's very straightforward regardless of the name of the model that you choose, it also provides a good context for each item. We can interpret it similar to the linear models that we've seen, but beyond that, it is more specific for each item than a label that may or may not apply, because there are different types of parameterizations for some of the labels that we will see in psychometric models. So now we have to specify the distribution for each latent variable after we've figured out the Q matrix. And typically, the most common distribution you see is a normal distribution. Model families with normal distributed latent variables include confirmatory factor analysis, item response theory, and something called enfolding models, which we won't cover much in this class. Typically, you don't see many other distributions. Wait for the next slide. I'll talk about a few cases. But when we specify this distribution, the distribution of the latent variables is the same as specifying a Bayesian prior distribution for the latent variables. So this distribution is serving as a prior for each person's set of parameters in our models. And then the other thing I want to note, because we're talking about each latent variable following a normal distribution, if we say a set of latent variables, so in our case, in this example from today's slides, 2 latent variables, if we say that they're multivariate normal, right? So now we have a multivariate or bivariate normal distribution for our latent variables. That's similar to saying that each latent variable by itself, marginally, is a univariate norm, follows a univariate normal distribution. So this multivariate normal distribution is very convenient for a lot of what we do, and we're going to end up using it for almost every single case of the analyses that we'll have from now through the end of the semester when it comes to the latent variable side. Now, there are some cases where other distributions get used because, as you know, if this is a prior distribution, you can use any prior distribution you'd like for any type of latent variable. Now, I will say that not many have been used because not many have been shown to be useful. For instance, we could define a Poisson distributed factor if we really wanted to. I don't know how useful that would be, but we could do that. The interesting part of this is that care is needed if you use non-normal distributions because there's some odd effects that could happen, particularly bias and other parameters, depending on how you specify those distributions. So you can see it from time to time. It does happen. However, if you're thinking, oh, I'm going to try something new, do look at those parameters, do look at the data, do compare with a normal distribution so you can get a sense for what's happening. Two clear cases of where non-normal distributions have the most prevalence, at least in my opinion, are Bernoulli or multivariate Bernoulli, if you want to have multiple latent variables that are used in a field called diagnostic measurement, diagnostic classification models, or cognitive diagnosis. Or also we see multinomial or categorical, depending on how you prefer to call it, distributions used in finite mixture models. Finite mixture models include latent class models, latent factor models, and so forth. So you do see some categorical latent variables show up in these distributions, but I would say by far normal and multivariate normal are the most prominent. Probably 95 to 98% of anything I've ever read include those. To a much smaller extent, you see these categorical latent variables, and then a little bit smaller than that, you see any other type of distribution, such as beta or otherwise. So let's talk a little bit more about the multivariate normal distribution. Multivariate normal distribution, we would typically just say, oh, theta, the vector theta p, so each person's theta, which is their set of latent variables, would say follows a normal distribution. Sometimes we put this little d subscript defining the number of dimensions of the normal distribution. So the number of dimensions is the number of latent variables. In our example for today, 2. Then the normal distribution is characterized by two sets of hyperparameters, or parameters, a mean vector, mu, theta, and a covariance matrix, sigma and theta. So I just want to give you a sense of the multivariate normal distribution. This is the distribution function. It functions just like all the other PDFs in that if we have a value for the mean vector and we have a set of values for the covariance matrix, then for any theta that we plug in, what this calculates is the likelihood or the density of that value, the height of the curve. In this case, it's a multidimensional curve. In 2 dimensions, it would look like a bell, effectively. This is very difficult, can be a very difficult distribution computationally. It's not always straightforward to take what's called a matrix determinant, which is right here, or a matrix inverse. So there are some catches that we have to do when we're building this underneath the hood in the computer algorithm, but it is a very useful distribution for what we end up doing. Now, the other key part of this is that when we say a latent variable follows a normal distribution, now we have to set its scale, right? We have to figure out its mean and its mean vector and covariance matrix. But it's actually a little bit more complicated than that. Psychometric models require 2 types of identification to be valid. The first type of identification is something called empirical identification, which basically says what is the minimum number of observed variables or items that you must have to measure each latent variable. So from confirmatory factor analysis, we can show that based on some assumptions of the model, in fact, if we look at the model assumptions marginally, we look at what it's saying about the data without conditioning on the factors, it says the data should follow a multivariate normal distribution. So in that multivariate normal distribution, we know how many parameters are present. And so what we have to do is to make sure that the number of parameters in our model does not exceed the number of parameters in that multivariate normal distribution for the data. And to do that, basically we need 3 observed variables for each latent variable by themselves. Or if you have multiple latent variables, one of those latent variables needs 3, and the others need 2, and the latent variables need to be correlated with each other. So it's a set of minimal constraints. Now, complicating all of this, though, is Bayesian estimation. Bayesian estimation can take things that are unidentified and make them look identified through the use of prior distributions. So for instance, I just, before this class, ran an example where I took 2 items and I used a unidimensional or single latent variable model. So it's clearly violating these 3 observed variables. The model had a little bit of an issue with convergence, but with a few changes to prior distributions here or there, I got results and I got numbers. The problem is I don't trust those numbers. It's very difficult to believe what's coming out when you don't have a lot of data. I also then took the most extreme example. I had one of our items and I measured it with 1 latent variable. Now think about that. We have 1 piece of data. How could we ever distinguish a latent variable from it and the set of item parameters themselves? We can't. There's no way to disentangle a person says 5 on an item, oh, their factor score must be 3. Now, that doesn't work. We have to know a whole lot more than that to make the model work. So my recommendation is always to use the standard that's used in CFA. 3 observed variables for each latent variable is a great minimum number. Now, if you're interested in measuring that latent variable reliably, you'll need many more items than that. So often, empirical identification is not an issue in educational measurement, where our goal is to measure latent variables as precisely as possible. It does, however, turn up from time to time in other use cases when the latent variables, we may not be interested in the scores as much as we're interested in the relationships between them and other constructs, such as instructional equation modeling. The other type of identification in a latent variable model is scale identification. Basically, what the mean and variance is for each latent variable. Now, I will talk more at length with this next week in the next set of lectures when we start coding what we're talking about here. But basically, there are 2 broad sets of this scale identification. One is to fix the values of the means and the variances. That's called standardized factors. So we set all the means equal to 0, we set all the variances equal to 1, and we estimate all unique off-diagonal correlations in the covariance matrix. The alternative to that is we can set what's called a marker item. So we set the value of a loading or a slope to 1 for one observed variable per latent variable. And then because of that, because of the way the math works out, we can then estimate the latent variable's variance, which is on the diagonal of sigma. For the means, we could do the same feature. We could set the item intercept to 1 for observed variables, item intercept to 0 or to 1 for one observed variable per latent variable, and then we can estimate the latent variable's mean itself. Now, there's different rationales for using either. If you're looking to put people on a common metric, standardized factors works just fine. If you're looking to do something with your latent variables, however, marker items are needed. For instance, if you have a latent variable and you predict it simultaneous to your measurement model, as in a structural equation model, you will need a variance for that latent variable model that can be different than a constant. Right? You are explaining that variance. It will not be 1. So that's why we might see the marker item technique. Similarly, often in measurement and variance studies, we may need to adapt the means for each, or estimate the means for each latent variable, at least some estimate of it as well. But the big picture in either of this is that either of these choices of marker items or standardized factors lead to the same data likelihood function. That is, the parameters that you receive with a given choice are transformations of each other that lead to the same likelihood value if you were to look at the most likely values of them. So this is telling us that it's a choice that we're making, but we're not necessarily changing the way the model works overall. So this is the big picture that I put right here. The important point is, regardless of model choice, model data likelihoods are equivalent. Now, the thing that starts to get us a little bit weird in Bayesian is our choice of prior distributions, particularly on the item parameters, may make models non-equivalent. But we're going to leave this as is for right now. So to summarize this lecture, for all psychometric models this semester, we're going to use multivariate number of distributions for latent variables. We will see both standardized latent variables and marker items, and we will form our models using our slope-intercept parameterization. Now, I will note in some of those models that we get into, particularly item response models, we can then change our parameters into discrimination difficulty parameters using stands generated quantities. They're all transformations from each other. So next step, we will be looking at how this works for a single latent variable. We'll be talking about model characteristics associated with each type of distribution we assume for our observed variables. And we'll talk about estimation of multidimensional latent variable models as well. Thank you for listening. I hope this recorded, so I don't have to do this a third time. And hope you have a pleasant rest of your day.